Hello everybody, this is Zareian from Power Electrical Developing Advanced Research Group. In this short training video, I'm gonna talk about dynamic coordinated GEP and TEP. Actually, in this video, I'm gonna talk about coordinated generation expansion planning and transmission expansion planning. In this video, we will talk about modeling of GEP and TEP when we want to coordinated optimization between these scenario of expansion planning. Like the previous training course, I would like to talk about this simulation and this issue using the reference paper that you will be seeing in this video. As you can see here, the reference paper talk about multi-objective, multi-year dynamic generation and transmission expansion planning, incorporating renewable energy resource. Actually, the main question in this paper is here. Where is the best scenario of the generation expansion planning and where is the best scenario of transmission expansion planning? Actually, we will talk about where is the best place, where is the best capacity for each type of generation expansion planning and transmission expansion planning. Before I want to talk about the simulation of this issue, I would like to talk about mathematical problem formulation which is discussed in this paper. As you can see here, the mathematical problem formulation of this paper is a start in page number 5. As you can see here, the total objective function of this issue is consist by two sub-objective functions. The first sub-objective function is related to the investment cost and minimization of investment cost. For example, the first part of sub-objective function number 1 is related to the cost of generation expansion planning, and the second part of the objective function is related to the cost of transmission line. Also, you can see all of these details related to this objective function from equation number 1.1 to equation number 1.19. So all of these details is discussed in detail in this problem formulation. The second objective function that is considered to minimization by multi-objective method is related to the objective function or index of ENs as a expected energy not served. So the objective function, the second objective function that is discussed in this paper in equation 2.1 to equation 2.9. So you can see all of these details to calculation of the ENs index for second objective function here. There are another tasks that have been done in this paper related to the novel multi-objective optimization that is discussed here. So, however, this problem is not necessary to discuss here because the main concept of this video is related to the planning of generation and planning of expansion for transmission. The flowchart of process of generation and transmission expansion planning is discussed in the flowchart of figure 2 in detail, so you can see all procedures of the generation and transmission expansion planning when we want to dynamically coordinated generation expansion planning and transmission expansion planning. As a case study, IEEE 16 bus of the network incorporating with renewable energy, different type of renewable energy is considered to check the and validation of the proposed mathematical optimization method for generation and transmission expansion planning. Also, different type and profile of the load for different years of the study is discussed in table 1, and different peak load ratio for each sub period is talked in table 2 and 3. Also, you can see different details of the generations unit, and the transmission line is uh, discussed in table 5 and table 6. Also, you can see different results for this simulation, and different scenario of generation expansion planning with different type of generation expansion planning, with different type of the transmission expansion planning, and different scenario of these is discussed in table 8. In order to simulation and talk about the simulation of this paper, using this paper scenario, let's go to the simulation result. You can see different objective function and different file of the simulation that is used for this program. By open the IEEE 60 bus as a main file of simulation, you can see different aspects of simulation here. For example, as you can see, the matrix of bus data here and matrix of line data here. Also, you can see different limitation for limitation and generation limitation here and gen data here. Also, you can see the generation and transmission expansion planning. For example, in this simulation, we have six type of generation expansion planning for different type of capacity, FOR as a failure of rate, and investment cost, and maximum expansion planning for generation for each type of the generation expansion planning. Also, we have two type of transmission expansion here in this matrix, and you can see different details about this expansion for transmission line. As in first part of the simulation, we start to run the power flow for system to calculate the parameters of system and objective function of system for transmission cost and power loss, and also generation cost of simulation without any expansion in power system. So in the first part, we start the simulation without any generation or transmission expansion planning. In the next step, as you can see here, we start the MOGA algorithm as a multi-objective generation, multi-objective genetic algorithm for finding where is the best scenario of generation expansion planning. Also, where is the best location of expansion planning. Also, where is the best scenario of transmission expansion planning, where is the best location, where is the best capacity of transmission expansion planning. So we consider six scenario of expansion planning. Actually, in this simulation, in this study, we consider 6 plan of generation expansion planning and 1 plan of transmission expansion planning. However, as you can see here, the main question is here: where is the best location, where is the best capacity, and where is the best type of expansion planning for generation and transmission. So we consider the independent parameters. The first parameter for each scenario between 1 and 6, that is related to the generation expansion planning, between scenario type 1 and scenario type 6. As you can see here, we have 6 type of generation expansion planning. So we consider where is the best scenario, where is the best scenario of expansion planning, and where is the best location, And another parameter is related to the number of scenario, one between 0 and 10, that is related to the how number of the scenario is the best number for generation expansion planning for each scenario. So three parameters. The three first parameters is related to the type for scenario expansion number 1. The second three number is related to the scenario of generation expansion planning number 2 or etc. Also, finally, we have the three independent parameters related to the transmission expansion planning, because we have one transmission expansion planning. Where is the best location for transmission expansion planning? Where is the best scenario? Where is the best location? Where is the best scenario? And where is the best number of transmission expansion planning in this system? The total objective function is defined here for multi-objective optimization. So you can open this total objective function here. As you can see here, if you open here, you can see the different type of load ratio for dynamic load. So you should define the best scenario of transmission and generation expansion planning for different level of the load, for load ratio of coefficient factors of the load for number 1, 0.75 and 0.6 as a different load ratio that is considered in this simulation here. So as you can see, at each you should select the best scenario of generation and expansion planning and transmission expansion planning for different load ratio, and you can calculate this cost. For example, the first objective function is consider generation cost and generation cost 2 and line cost for different type of the cost that is used for expansion planning, for old generation cost and new generation cost expansion. Also, you need to consider objective number 2 for ENS index. As you can see here, the ENS index is calculated here for different scenario of ENS, and you can see the second objective function, and the total objective function is related to the first objective function and second objective function. As after you run the simulation, you can see the result here for six scenario of expansion planning. Where is the best scenario type of, where is the best type of GEP number 1 is the scenario type of 3, as you can see here, for example, number 3 with this capacity. Also, you can see the best location is bus 11, and the number of GEP for scenario type of number 1 is related to three number of scenario type of expansion planning number 1 at bus 11 with scenario number 3. For another also, and like this scenario, for another scenario of GEP can be seen, you can see here. Also, the best type of TEP is scenario type of TEP number 1 at location line 20. Bye for now.